Qspeed diodes get performance similar to silicon carbide Schottky diodes with a standard silicon process. This makes them great for power supplies and other hard switching applications where low losses and soft recoveries are important. To learn how they do it, let's quickly review the device physics behind several types of diode junctions. Then we'll see how Qspeed diodes use both the Schottky and p-intrinsic N structures to get the best performance. When a silicon p-n junction, consisting of a positively doped p-type semiconductor and a negatively doped n-type, is reverse biased, the free holes and electrons of each material are attracted to either pole, leaving behind an empty section called the depletion region. Because there are no free carriers in this region, there's no path for current to flow through the device. So the p-n junction blocks current flow in the reverse direction. When the p-n junction is forward biased, the depletion region disappears as carriers are repelled from their poles. This provides a path for current to flow through the diode using the majority carriers in both materials. Remember that positively charged holes flow in the direction of conventional current and electrons in the opposite. When they reach the p-n junction, most majority carriers recombine with their opposites, providing a net energy transfer that facilitates current flow in either direction you visualize it. But some carriers get through the junction without recombining and continue to drift into the opposite material, also carrying current with them. These are called minority carriers. When the diode is reverse biased again after conduction, the depletion region needs to be re-established to block current. Before this can happen, most minority carriers must be removed from both materials. They have to travel all the way back to the junction. Some will recombine along the way, others at the junction, and the rest will return to their host material. This takes time and carries current backwards through the diode. It's what causes reverse recovery losses in p-n junctions. Schottky diodes made from standard silicon or high-strength silicon carbide only have one type of semiconductor material, swapping the p-type for a metal contact instead. Because the carriers in both the metal and the n-type silicon are electrons, the Schottky diode is strictly a majority carrier device. When it's forward biased, current is carried all the way through by electrons only, with no minority carriers moving in the opposite direction. When the Schottky is reverse biased, electrons are pulled towards the positive pole, again creating a depletion region to block current. Because this region is extremely small and there are no minority carriers that need to travel all the way back through the material, the Schottky diode can recover much faster than a p-n junction. In fact, reverse biasing a Schottky is essentially like discharging the plate of a capacitor. Discharging this capacitor is much faster than waiting for the recombination and recovery of the p-n junction, reducing reverse recovery current and cutting switching losses by more than 80%. This fast, capacitor-like recovery is the reason Schottky diode losses are labeled QC instead of the traditional QRR. And with sub-100 nanosecond recovery times, Schottky diodes often allow designers to more than double switching frequency, significantly increasing power density in their designs. Unlike standard silicon Schottkys, which are limited to a breakdown voltage of about 200 volts, silicon carbide Schottky diodes can easily work at 600 volts and above. They bring fast recovery and reduce switching losses to very high power designs. Silicon carbide material is also expensive, often pricing this performance out of reach for normal designs. A less expensive way to achieve good performance with standard silicon is the p-intrinsic N diode. The PIN junction uses a lightly doped N-type semiconductor sandwiched between two regularly doped P and N-type sections. This drift region significantly increases the breakdown voltage of the device. It's also typically injected with platinum ions or other materials that act as recombination centers to help reduce minority carrier lifetime. When the diode is forward biased, the voltage drives carriers to diffuse through the intrinsic material and carry current through the junction. When it's reverse biased, minority carriers are attracted to the nearest recombination center in the drift region, where they can quickly find an opposite carrier to recombine with, creating a much faster recovery. This allows PIN diodes, commonly referred to as ultrafast diodes, to have much lower reverse recovery losses than a standard p-n junction. But the larger junction thickness brought by the intrinsic material requires a much higher forward voltage to drive the same amount of current, causing increased conduction losses and lower efficiency. Qspeed diodes solve this problem using three-dimensional mechanical features called P-wells, offset by Schottky contacts, to get the best of both pin and Schottky junctions in the same device. Using specialized masks and vertical doping techniques, tubular trenches of P-type material are injected into the N- material. The conduits to these trenches are surrounded by a non-conductive insulator so that carriers can only flow through the surface area boundary of the trenches themselves. A metal contact is then deposited along the entire section, forming a Schottky contact with the N- material in between the P-wells. So Qspeed diodes are both Schottky junction and P-intrinsic in at the same time. When the diode is forward biased, the Schottky junctions conduct immediately, and electrons flow into the channels between the P-wells. As the diode conducts more and more current, the voltage in the channels begins to increase, until it becomes so large the P-wells start to inject holes as well. These holes recombine with the electrons at the channel entrances, directing all carriers through the P-wells. When the diode is reverse biased, it enjoys both the fast reverse recovery of the Schottky sections and low minority carrier injection losses from the pin effect, providing an extremely fast, low-loss recovery. Once the recovery is complete, the P-wells create strong, overlapping electric fields that pinch off the Schottky channels, preventing leakage current through the Schottky junctions. This allows Qspeed diodes to withstand a reverse voltage of up to 600 volts, while standard silicon Schottkys usually break down at only 200 volts. Variations in the length of the Schottky channels lead to different P-well conduction voltages, allowing design trade-offs between lower conduction losses and softer, more efficient recoveries. This leads to our entire Qspeed family, with diodes customized for every application, like the softest Q series, lowest conduction loss X series, and lowest switching loss H series. Their innovative construction helps Qspeed diodes eliminate more than 80% of switching losses seen in ultrafast diodes, while maintaining excellent softness to reduce EMI noise. That's performance similar to silicon carbide Schottkys in a standard silicon process. For more information on Qspeed low-loss, high-voltage silicon diodes, visit the Power Integrations website at www.power.com/Qspeed.